All right, so that's good. It's recording. All right. So are there any questions about the homework assignment?
Yes, how you doing?
Watch the video from last class meeting. Well, you have to get started with understanding the concepts first. Beginning with that. The two mysterious lines are one is dot int L1 plus 4, and the other one is dot int L1 minus 6 or something like that.
4.
Yeah, minus 4. Okay, but start with those two lines. You have to understand what those two lines are actually doing. And in order to understand those two lines, there are two ways to do it. Let me just go ahead and bring up the file so that we can talk about it. M2, MS, just open it. All right, we'll go ahead and change the font size to be a little bit bigger. There we go. Okay, good large font here. All right, so the first thing you have to do is to take a look at or understand what lines 3 and also line 6 are doing. Those two lines are the most important lines because they're one of the most important lines. But you have to understand what those 4 bytes are. When we say the two dot ints. Okay, so start with those, and you can test it too. I mean, you can just go ahead and comment out line 12 to line 16, so the program would at least assemble, and then put a breakpoint, right after the after, because all you want to do is to look at the memory content when the program is first loaded. And I would just first look at the memory content at this location, line 6, and also at this location, line 3. Those two lines, are important. And also keep an eye on the objective of your program. The objective of your program is to put the value of hexadecimal 400, there's an implied leading 0, okay, so it's 0400 into the register ECX, which is the a window into the lowest 16-bit of the register ECX, okay? But that part is nothing mysterious because you can see the last instruction has a destination register of CX. So we know that we are only dealing with CX as the last instruction anyway. So there's nothing mysterious there. So the next question is, what does this has to be, or what is the location that this operand has to specify in order for you to end up with 0400 in CX on line 16? And then you work your way back to figure out what the underscores and the other parts of the program has to be in order to get this to work. So are there any questions? No questions? So this is an interesting exercise. It does make you think about all the addressing modes and also what it means when we have something like this. Now remember I said there are two ways to look at these two lines, line 3 and line 6. The first way is to use the debugger. Use the debugger and then use the X command so that you can actually dump the content out from those two locations. And I would dump them out as 32-bit hexadecimal values. Okay? And I would also compare the values at those two locations with the value of L1 itself. Okay, so look at L1 itself, which is just print L1. It will show you the value of L1 as a label, and then compare that to the values at those two locations. Okay, and then from there, it's just a matter of time before you figure out how to initialize or what to specify with the underscores before you can, and get the program to work. Any questions? Now, when you work when you work on this program backwards, you can always, now before you turn it in, you can always add additional instructions. Just make sure that you make a little mark, on your own instructions, so that way you can inject values into EAX and EBX to help you debug your program. So you can basically quote unquote jack it so that it will give you the result that you want. So at least you can verify if I initialize EAX to blah 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 and EBX to blah 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 and specify this underscore to be blah blah blah, I will at least accomplish the result. And then from there, you can work backwards and see if you can how you can initialize EAX and EBX to the right values. Any questions? No questions? All right. Now, you have another week to work on this one, but it will take you another week to work on this one. So I would definitely try to get started as soon as possible. As I always tell my 6th grader, if you get started early, does it mean more work?
Is it due on Tuesday?
No. Is it? I think it's due on
Thursday.
Due on Thursday.
Yeah, that's Thursday.
Oh, that's today. No, that's
2 days.
That's, oh, okay. All right, so you have another 2 days to work on it, I guess, instead of another week. I thought today is a Thursday already, and that's next Thursday. All right. So we are good with this homework assignment? But get started with it early as possible, and follow the hints that I mentioned. Look at those 2 locations, because that's the key to get this homework assignment done. And also make sure you understand all the addressing modes, because the homework assignment is designed so that you have to understand the addressing modes in order to get it done. So that's definitely a key component to get it done. All right. So I'll just leave this up in case anyone has any questions, but we'll move on to continue to talk about the stuff that we talked about last time, which is adding. I'm not sure whether we are done with adding itself or not. We'll go ahead and see how far we went from last time. Does anyone remember how far we have gone with this note here? No one? It's okay. Okay. So we talked about the last carry bit, and as it turns out, the processor keeps track of the last carry bit. Even though it is not stored as a result of an addition, it is actually stored as a flag. Okay, we'll talk about what a flag is later on, but it is remembered by the processor. In other words, if you ask the processor, in the previous add instruction, is there a carry of 1 from the most significant bits? The processor can tell you, yes, there is a carry of 1, or the processor can tell you there's a carry of 0. Okay, and that comes in very handy and also important when we talk about subtraction. The next thing we also talked about is the result 0. In other words, we are basically just taking, this is actually incorrect, it doesn't render correctly here. Basically you have the summation, all bitwise ORed, and then you have a bitwise NOT on top of everything. And the result is the Z flag, which is also a flag, is just a bit, 0 or 1. But Z is a 1 if and only if the result of an addition is 0. Okay, and that's why it's called a Z flag, which means 0 flag. Okay, the 0 flag is a 1 if and only if the result of an operation gives you 0. And these are not as important at this point as later on, because when we talk about subtraction, these flags will become far more important. What we'll do now is to talk about 2's complement. In other words, how do we represent negative numbers inside a computer where everything is binary? Okay, how we represent negative numbers is doesn't seem to be a very complicated question, right? I mean, in decimal, when we write negative numbers, all we have to do is to say 56, this is positive, and if we want to negate it, it's just negative 56. We just put a negative sign in front of it, and the number becomes a negative number. Well, we have a problem. We cannot use this mechanism when we only have zeros and ones. In other words, internal to the computer, internal to the memory of your computer, you can only store zeros and ones. There's no minus sign that you can store. So one thing people would say, well, but that's okay, because I can just use whatever 56 is. I can represent 56 as a binary number. Okay, so let's take a look at 56. I'll just do it on using a notepad here, so I don't have to deal with a whiteboard. All right, so 56 in decimal Okay, that makes it very explicit. It is a base 10 number. In binary is 3 times 16 plus 8, right?
Yeah.
Okay, here's the 8, and then here's the 3 times 16. So I think that's 56 in binary as an 8-bit number. In fact, I'm sure it is. Okay, there are two ways to look at this. This means times 8 because we have 3 zeros for the least significant bits. It means times 8 because 2 to the power of 3 is 8, and 111 is 7, represented as a binary. 7 times 8 is 56. Okay, so I just want you to know kind of like all these little tricks so you can do the conversion quickly in your mind. Some numbers like this one is easier. Any number that has 8 or 16 as a factor, those are pretty easy to do conversion because you just have a whole bunch of zeros as the least significant bits. Numbers like 31 is really easy to because it's very close to a power of 2. 31 is 2 to the power of 5 minus 1. So that means if you want to represent it as a binary number, it will be 11111 because it's 2 to the power of 5, which is in binary 1 followed by 5 zeros minus 1. Okay, anyway, so some people say, well, if we want to represent negative 56 in base 10, maybe we can just use the most significant bit to indicate the sign of the number, and as a result, we'll represent this as 1, 111, 0, 0, 0 in base 2. Okay, that's one way to represent it. Okay, but this representation has problems. Okay, the biggest problem with this type of representation is now you need a whole different way of adding integers. In other words, I can't really add a negative value to a positive value using a regular add mechanism. I cannot do that anymore. I have to look at the sign flag, which is the most significant bit in this case, and say if it is a 1, it means the value is negative. So instead of adding, now I have to subtract. Okay, so you have to go through a lot of logic to make this representation work. The representation itself is not a problem. You can, if you choose to, represent numbers this way. There's another problem with this representation. The value 0 gets represented twice. Okay? Because 0 as an 8-bit number is simply 8 zeros, right? But it is also, you can also use this representation because this means negative 0. Negative 0 and just positive 0, they both represent exactly the same value. In other words, you're wasting one bit combination to represent the same value twice. Okay, that's another problem with this representation. So we don't like this representation because of these problems. So instead of doing this, we'll use another way to represent negative values. It's called 2's complement. Now, according to the notes, I have a special notation. 2's complement, which I use C2 to represent 2's complement. 2's complement of x is basically taking the bitwise knot of x and you add 1 to it. That's 2's complement. Let's go ahead and do some examples here. Well, let's go ahead and do it to, say, 56. Okay? What is the 2's complement of 56? Well, we apply the bitwise knot operation to 56, and then we just add 1 to it. But what is bitwise knot? I cannot do bitwise knot to 56 as a decimal number. Why not?
Because you can't flip the bits because they're not bits.
Because they are not bits. What is a bit? What does bit mean? It's an abbreviation of something. What is it? It's a binary digit. Okay, the B comes from binary and the IT comes from digit. So I cannot do a bitwise knot, on 56 as a base 10 number because it is not in binary. I can only do bitwise knot to binary numbers. Well, that's not a problem. I can do the base 2 conversion here, which turns it into 0, 1, 1, 1, 0, 0, 0 in base 2. And this is the other thing you have to pay attention to, is when we perform bitwise knot and 2's complement, you have to specify the width of the operation. In this case, we're dealing with 8-bit numbers. Okay. And what do you think bitwise not means? It's basically the tilde operator when you talk about C and C++. What does it do? What is a bitwise not?
All the zeros to ones and the ones to
Exactly.
zeros.
It's a negation, but for each bit position. Okay? You know about the exclamation point, right? The exclamation point in C is a logical not. You know, if you have 0, and then you use an exclamation point 0 is non-zero, which means true. Exclamation point non-zero is 0, which means false. Not true is false, not false is true. But in this case, we are doing the same operation for each bit position. So can someone tell me what is the result of the bitwise not of 0, 1, 1, 1, 0, 0, 0? We turn all the ones into zeros and all the zeros into ones, so it becomes 1, 0, 0, 0, 1, 1, 1. You base 2, and then we have to add 1 to it.
A spot that's only 7.
Oh, I'm missing
Yeah,
1.
leading 1.
I'm missing 1 over here, so I'm missing.
You're missing the leading 0.
Yeah. Trailing.
No.
Is-
No?
Oh.
Leading.
It's 7-bit right now.
Yeah.
So we need
Yeah, so I need to fix that one too. Because I want everything to be 8-bit. Okay, so there you go. Okay, now we are all fixed here. So this will become 1, 1, 0, 0, 1, 1, 1. Okay. Is everything good?
Yep.
Okay. And, you know, without using your calculator, can you guys tell me what is the result of this addition?
1, 1, 3, 1, 1.
Right? All right. So this bit pattern here, 1, 1, 0, 0, 1, 0, 0, 0, I claim that this represents the value of negative 56. Okay? Whereas the other pattern is this bit pattern here represents 56. Tell me something, you know, some properties of negative 56 as a value, as opposed to 56. What can I do to it to, you're like, okay, can we check whether this is a valid representation of negative 56? How about adding these two bit patterns together? I should get 0 back, because one represents the value 56, the other one represents the value negative 56. If I add those two bit patterns, the result should be 0. Does it make sense? So let's check that and see whether, you know, we get back to 0 or not in this case. So on one side, I would use, you know, base 10, and then on the other side, I would use binary. Okay. So 56 is 0, 0, 1, 1, 1, 0, 0, 0. In base 2, I'm not, you know, going to use the paren 2 anymore, you know, just because, you know, it is pretty clear that we are dealing with base 2 number here. And then negative 56 is represented by 1, 1, 0, 0, 1, 0, 0, 0. And we'll just do a quick addition here. I don't think I have to explain this one. I hope not. And then here, you know, this one is pretty easy too. You know, 0 plus 0 is 0. 0 plus 0 is a 0. 0 plus 0 is a 0. This is a 0, but it has 1 carry. Okay? So that means this is a 0, 2 with 1 carry. This is also a 0 with 1 carry. This is a 0 with a carry. This one is a 0 with a carry. And this ends up with a 1. Oh, uh-oh, that's not 0. But remember what I said a little bit earlier? When you do bitwise not and 2's complement, what do you have to take care of? The width of the operation has to be fixed. So in this case, because the width of the operation is 8-bit only, this carry flag here is not a part of the result. It is stored, but it is not a part of the result. So that means the result of the operation is really just this part, and that turns out to be 0. Is that making sense so far? Question?
So it's a trick of scope to get your result rather than an actual additional result.
It is the addition result because your ALU has a fixed width.
Right.
And as a result, and also when you store something back into memory, if you're dealing with 8-bit operation, you can only store the least significant 8 bits back into memory, even though there's a carry of 1 in the end.
Okay.
Yep, go ahead.
How can you tell the difference between a number that's negative and a number that's just like?
That's a very, very good question. We'll get to that. If I don't get to it, remind me, okay? That's a very good question. Yep.
Same as him.
Same as him. Okay, very good. So we'll get to that question later, okay? But before we move on any further, maybe some people would just say, well, maybe you just, pick 2-bit patterns that just so happens to work out in the end. So we'll try something else, okay? We'll keep negative 56, but we'll add it to a different value. What do you want to add negative 56 to? So that we.
How about
Well, how about
57?
something less than 127? Less than or equal to 127?
57. Add it to 57. Add negative 56 to 57.
Negative
56.
To 57.
to 57.
Yeah.
Okay, so, all right. So in that case, we have 57 here, right? Are you sure this is going to be quite boring?
Yeah, let's do let's get a negative number. Let's do like 40 or something.
Do you want negative 40 maybe? Do you guys want to see what is negative 40 plus negative 56 and confirm that it is actually a valid result?
Yeah.
That's actually a very, very good example because the question is, how do we know the end result is representing the proper value? Okay, that's a very good,
Negative 44.
okay. Negative 44, okay, fine, negative 44.
46 is the meaning of life, right?
Yeah, but we'll just get close to it.
It's Valentine's Day. You don't need to get deep.
All right, negative 44 it is. Now the question now is, okay, we want to add negative 44 to negative 56, but we want to do everything in binary. So the first thing we have to do is to figure out how do we represent negative 44 as a base 2 number. And to do it, like this, we can use 2's complement. You can look at 2's complement as arithmetic negation. It is the same as putting a minus symbol in front of a value. You can do it to a negative value, you will end up with a positive value. You can do it to a positive value, and you end up with a negative value. Okay, that's the trick. In fact, if you apply it to 0, you should get 0 back. Okay, we'll double check all of that stuff later. But first of all, we'll just do this one here. So we have a bitwise NOT of 40, and 40 is 5 times 8 plus 4. So 5 is 101, and then here's 8. But we have to add 4 to it. So here's the 4, and we have to pad zeros on the other side. This should be 44 in base 2. Okay, there's another way to check it because 44 is 11 times 4, right? 11 is this. Times 4 is this part. Every time you want to multiply a value by a power of 2, you're basically padding the number of zeros on the right-hand side, which is the power of 2 that you're multiplying. In other words, when you multiply by 1, which is 2 to the power of 0, you're padding 0, 0 on the right-hand side, which is fine. If you multiply by 2, then you're padding 1, 0 because 2 is 2 to the power of 1. When you multiply by 4, then you're padding 2 zeros. When you multiply by 8, you're padding 3 zeros, and so on. So this way, I can quickly verify that my result is actually correct. Plus 1, and then we can do the bitwise NOT first. So it's 1101 0011 plus 1, and then we have 110 10100. Okay. All right. So now we want to do the actual calculation. So on one side we have the base 10 version of the addition, and then on the other side we have the binary version of the addition. So in this case we have 1101 0100. Whoops, take it back. Wrong row. Okay, this is 1101 0100, and then the other one is the same as last time, which is 1100 1000. So now we'll go ahead and add these two numbers. What is the base 10 version of this?
Negative 100.
Negative 100. And the binary version is going to be what? Well, this one I actually have to do some calculation. 0 plus 0 is 0, 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 0 is 1, that's 0, that's a 0 with a carry, that turns this into a 1, and then plus 1 at the very end, but that 1 is not stored, it is not a part of the result. Since it's not a part of the result, we'll just kind of, I'll put it in parentheses. So this way it is clear that it is not a part of the result. In other words, the result of the addition is this particular bit pattern. So so now the bigger question is, well, this is just a random bit pattern here. So how do we know that this bit pattern is actually representing negative 100? Right? I mean, I'm just giving you some bit pattern here. I mean, I could have chosen any bit pattern. So how do you know that this is actually representing negative 100?
Subtract 1 from it.
Subtract 1 from it. How about I apply 2's complement to it?
Okay.
If this is representing negative 100, what happens when I apply 2's complement to it?
It should be a positive.
It turns it back into positive 100 because 2's complement is the same thing as arithmetic negation. Okay? So now let's do that to see what we are getting back here. So we have 2's complement, this time applied to a binary number to begin with. So that should be relatively easy to do. Okay? The first thing we do is to do a bitwise NOT, and then plus 1. The bitwise NOT is going to be 0, 1, 1, 0, 0, 0, 1, 1, and we add 1 to it, and it becomes 0, 1, 1, 0, 0, 1, 0, 0. Is that really 100? Well, let's do some really quick number here. We have 0, 1 here, 0, 2, 0, 1, 0, 2, 1, 4, no 8, no 16, 132, and 164. And that adds up to what? 100. Okay? It must be a fluke, right? I mean, maybe TAC just picks some really specific values so that this sort of thing just kind of works out, right?
Tricking us, Gypsy.
Yep.
Stay away from it.
Well, let's do it to 0, okay? Because what is negative 0? What happens when you negate 0 itself in arithmetic, not as a bitwise operation?
Stays the same.
You get 0 back, right? So that means if I do this, I should get 0 back. Well, let's figure out whether this is really the case or not. 2's complement applied to 0. And remember, this time we are dealing with 8-bit numbers, so I'm going to say 0 is 0, 0, 0, 0, 0, 0, 0, 0. Okay. And that's the same as bitwise NOT of the same bit pattern. Plus 1. The bitwise NOT of that particular bit pattern is 1, 1, 1, 1, 1, 1, 1, 1, and then I add 1 to it, and that becomes 1 followed by 8 zeros. But remember, this 1 here is not stored as a result. It is going to be stored as a carry flag. So yes, in fact, I get 0 back. So it looks like 2's complement is a fairly useful operator because it is the same as negation in arithmetic.
So your 1 in parentheses is actually your Z carry, yeah?
Yeah.
Your Z flag. And
Yep.
then where does that get stored?
That gets stored in what we call a flag. It's basically just one single bit position in the processor, but it is remembered. In other words, after you perform an add operation like this one, it is remembered, and there are certain instructions that can read it back and say, oh, did we get a carry of 1 or a carry of 0 last time? So those instructions will become very, very handy later on. But for now, we don't know how to access the carry flag, but it is stored, it is remembered. All right. So now let's go back and answer the question that you asked a little bit earlier. Because we can look at, we can look at this bit pattern here. Let's look at 1001, 1100. We claim that this is negative 100 from here. Okay? This part, shows that, this bit pattern represents negative 100. On the other hand, we can also say, but it is also, what is the other representation? This 128 plus 64, 32, 16, 8, and 4. So that adds up to what? 156. Okay. Well, we have a little bit of an issue here. We have an identity crisis. It's an identity crisis because we have the same bit pattern. In other words, it is represented by the same states of transistors when you look at this from the perspective of your memory or even the registers. It's the same bit pattern. And we claim that it represents -100. We also claim that it represents 156. How can that be the case?
Flag.
Hmm?
There's a flag.
Well, it's not the flag.
Has to do 256.
It depends on the context. Okay? The bit pattern is just a bit pattern. It's nothing more than dots on printed paper. Okay? In other words, if you look at this bit pattern here as a signed char, it represents -100. When you look at it as an unsigned char, it is 156. All right. Well, then why do we even bother with signed versus unsigned when you program in C? I mean, since they have the same representation anyway, so why do we even bother? Well, we bother because when you compare numbers, then it makes sense. Are we looking at this as -100, or are we looking at this as 156? Because you can compare this bit pattern with 0 and say, is it greater than 0 or is it less than 0? Well, depending on whether it is a signed comparison or an unsigned comparison, the result is going to be different. Are we doing okay so far? So that means everything that you learned in C, where the variable itself tells you whether it is signed or not, you have to toss all of that out the window. Because in assembly language programming, a memory location is nothing more than a memory location. A byte location is just a place where you can store 8 bits. You can look at those 8 bits as a as a signed number. You can look at those 8 bits as an unsigned number. You can also look at the same 8 bits as an ASCII code that you can print out to the screen. There's no difference whatsoever. It's still the same 8 bits. Are we doing okay so far with that concept? Now we will encounter this again and again, so hopefully we'll just have more reinforcement later. Question?
No, sorry.
Okay. Are we doing okay so far with 2's complement? What is the advantage of 2's complement again?
You don't have to have a special way of handling the last bit, so you can just add and subtract.
Yeah, exactly. So that means signed addition works exactly the same way as unsigned addition. Okay? The only time when it is important or when it makes a difference is when you compare or subtract. Okay? Are we doing okay so far with this? Let me save this file because I'm pretty sure someone will want to refer to this again. Yep, go ahead.
Are you going to talk a little bit more about, like, you have a number pattern. How am I supposed to know if it's signed or unsigned? And then how am I supposed to know which ones in an unsigned and a signed number represent positive values and negative values?
Okay, that's a good question. Whether it should be looked, seen, or interpreted as signed or not, we cannot talk about it now because we don't have the instructions that makes a differentiation. The add instruction doesn't care. Okay, the add instruction says, you give me 2 bit patterns, I will apply the half adder and the full adder thing, the logic that we talked about last time. It's going to blindly apply that logic to the 2 input numbers and give you the answer, and that's it. And as it turns out, whether it is signed or not doesn't really make any difference because of the way we represent negative numbers. So the same addition operation will work in both cases. And that's why the add instruction, there's no signed add versus a unsigned add as instructions. It's the same add instruction. Subtraction, the same way. The subtraction instruction itself is actually the same thing. Whether it's signed or not, you're still using the same subtraction. Compare is the same. What is different is the flags that they set in the end. The subtraction or the compare instruction we'll set certain flags. There are 4 flags that we really care about in this class. So the question now is, what is your interpretation? Which flags do you choose to interpret when you need to say, I need to go this way if this number is greater than this number, and go the other way when it is not the case? That is your choice. That's when the signed versus the unsigned becomes important. But at this point, we can't really talk about it because we don't have the mechanism yet. Yep.
With the same number of bits, if it's a signed number, it can only represent half the range of values, right?
Correct.
So if you have 8 bits like you have there, which bit patterns are excluded as positive and which aren't? Like how does that go?
Okay, the most significant bit is called a signed bit for a reason. If it is a 0, that means the value that it is representing, the whole bit pattern is representing, is non-negative. If the signed bit or the most significant bit is a 1, and you choose to interpret the bit pattern as a signed number, then the value it is representing is negative.
So it's the whole range with the 1 following the beginning, and then that whole range is negative from that whole.
Correct. Now let's take a look at a simpler case. Okay, this is a wheel because that's how numbers are actually represented inside a computer. Okay, when you have 32-bit numbers, you just have a much bigger wheel. Okay, but we choose to use a 4-bit number in this case, and we'll go ahead and use our decimal representation first. So we have 0 here, and then we have 8 on the other side, 4, and then we have 12, and then we can just keep dividing in half. That's why it's easy to draw it, because you just keep dividing it in half. I'm going to turn on the light so it's easy to see this one. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and back to 0. Okay, that's a wheel. This is the wheel of a 4-bit number, because it only goes up to 2 to the power of 4 minus 1. When you have a 32-bit number, you just have a much bigger wheel, that's all. It's still a wheel, okay? The reason why I choose to use a wheel to represent numbers is because when you're adding, you're just turning it. When you're subtracting, you're turning it the other way, okay? And that's why you have a wrap-around problem. When you add 1 to the largest value that an integer can store, you get back to the least value that the same integer can store. Signed or not, that's going to happen. Okay, but from the wheel perspective, it makes sense, because if the number is, if there's a pin, pointing to 15, when you move that pin 1 over to the right-hand side, or when you rotate the entire wheel counterclockwise once, then you get 0. And that's how it works. So now let's look at the bit patterns here. 0 is easy, 0, 0, 0, 0. 1 is 0, 0, 0, 1. And the rest are fairly easy. 7 is 0, 1, 1, 1. 8 is 1, 0, 0, 0. 9 is 1, 0, 0, 1. And 15 is 1, 1, 1, 1. Okay? I'm missing a whole bunch of stuff in the middle because we can probably figure that out. Okay, so that's one way to look at the wheel. But you have another overlay of exactly the same wheel where you can represent negative values. Now, let's not worry about negative values on this end. What do you think this should represent as a negative value?
0, 0, 1.
No, what value should it be representing? It's right next to 0. This is 1, this is 0. So you keep going this way, what should this be?
Negative 1.
It's negative 1. Negative 2, this is negative 3, and so on. This is going to be negative 7, and this is going to be negative 8. Okay? But this is not going to be negative 9 because, and you can see all the negative numbers have a most significant bit of, oops, not this one. They all have a most significant bit of 1. Okay, and that's why that bit, the most significant bit, when you look at a bit pattern as a signed number, the most significant bit is also called a signed bit. Because when the signed bit is a 1, the value is negative. When the signed bit is a 0, it is non-negative. I would not call it positive because 0 is not positive. It's neither positive nor negative. Are we doing okay so far with this representation? So that means, yeah, we do have bit patterns here that can represent two different values. This side is okay, but this side has dual identity. You just have to choose the right instruction in assembly language programming so that you get the correct result. And remember, the only time it makes any difference is when you want to compare numbers. When you want to say, I want to compare number A to number B. If A is greater than B, I want to go this way. If not, I want to go the other way. That's the only time that it makes any difference whether it is signed or not. When you are adding two numbers, signed versus unsigned makes no difference. When you're subtracting, signed versus unsigned makes no difference. When you're comparing, it makes no difference. And that's because in assembly language programming, compare is one instruction, but to utilize the result of the comparison is another instruction. It's the other instruction that that needs to understand whether it is signed or unsigned. Are we doing okay so far with this? Yep. Go ahead.
Why is to the right side? Why is that side not why does that not have any negative numbers on it?
Because we only want one half of the wheel to represent negative values.
Okay.
And at this point, we have this half that can potentially be negative values.
Okay.
So that way you have exactly eight non-negative values, and you have exactly 8 negative values.
Okay.
So it's even.
That's all you. Okay, I understand.
Yeah.
I misunderstood what you were just saying.
Okay, that's fine. All right. Okay, so now we are done with addition. We kind of talked about signed versus unsigned. We talked about 2's complement. That's how we can do negation. And then the next topic is subtraction. How do we perform subtraction in base 2? No, I guess we'll talk about that later. Okay, now we have these flags here. The flags are kind of important. And let's see where we talk about the instruction itself, the add instruction. Okay, there we go. I almost skipped this one. But the add instruction is very, very simple to understand. If you know how to use the move instruction, basically copy, you know how to use the add instruction. The add instruction, just like a move instruction, has 2 operands. The first operand is always the source, the second operand is always the destination. Except in this case, the second operand is an implicit source as well. In this instruction, add L, EAX, EBX, we take EAX, we take EBX, we compute the sum of the 2. We store the result into EBX. Okay? So it's very, very similar to a move instruction, except instead of just copying, we are adding the 2 operands and then store the result in the second operand. The second operand is still the destination, it's storing the sum.
So it's like a plus equal, but it's going to the right-hand side.
That is correct. It's a plus equal, except it's the right-hand side that is storing the result, not the left-hand side.
Right.
Okay. Very good. And remember, the add instruction does not choose the interpretation. Whether it's signed or not, it's still the same add instruction. That's all I have to do. That's all I have to say about the add instruction, except for the side effects of the add instruction. We talked about the carry flag already. In other words, the carry from the most significant bit is stored in the C flag or the carry flag. So in this case, I have an example. If you put this particular bit pattern into EAX and then you execute this instruction, then EAX itself will become 0. But the carry flag itself will become a 1 because now we have a carry from the most significant bit of the addition. Is that making any sense? Let's check it. Let's see whether the assembler can confirm this. Okay. So we go to today's folder again. And we'll say test the carry flag. And we'll do exactly that. Okay, we'll put this particular constant into EAX, add long $1 to EAX, and we'll put a no op here so we can stop on the first instruction. And then we'll just go ahead and exit the program as usual. Like that. And I'm forgetting one thing. I think I'm forgetting a dot text, which is not necessary, but it's nice to have it there. All right, so let's go ahead and test this program. And we'll put a breakpoint on line 5. Okay, so run the program. Now we are about to execute this instruction. It's really just copying the bit pattern all ones into EAX. Single step, double check EAX has a value of FFFF, and in decimal sign interpretation, it is also representing -1. Is that surprising? No, because we saw that on the number wheel already, because 0 is right next to -1. All right, so we'll go ahead and execute the second instruction now. Okay, the second instruction is now executed. We look at EAX, it becomes a 0. Is that surprising? No? Okay. But we want to look at the carry flag, remember, okay? So the question now is, where is the carry flag stored? How do we display that? If you say IR, info register, it displays all the commonly used registers. And you can see when you look at E flags, the CF is the carry flag. In this case, when you see CF, it means the carry flag is a 1. Okay? In other words, if you want to, you can just say IRE flags, and that confirms that the carry flag is in fact set, which means the carry is a 1 from the previous addition. Yep.
So if there wasn't a carry flag, CF wouldn't appear there?
Correct. Well, we can test it easy enough. Okay, so we'll go ahead and change the program just a little bit so that it will not be the case. Add 0, right? If you add 0 to a number, the carry flag should never be set because there would not be any carry from the most significant bit. So we'll go ahead and test the program again. In fact, this time we'll go ahead and just stop on line 8 because we already know what the other lines would do. So put a breakpoint on line 8, run the program, look at E flags again, and you can see the CF is no longer there. Do we have any questions at this point? Yep.
Currently, do we need to know what PF, SF, IF, or ID is?
We don't, in this class, we don't need to look at all of those flags, but the sign flag is important, S flag is important, SF is important, CF is important, ZF is important, and there's one more called the overflow flag, OF, that's also important. So we'll talk about all of that later on today. All right. Are we doing okay with this? Oh, wait, there's more here. If I use this, okay, let me just go back and change the program to what it was before, because it was like this before. Because there's one more flag that we have talked about already that should also be set in this particular case. The 0 flag should be set. Yes?
I was going to question about the 0 flag being set when you first ran it.
Well, it wasn't set last time because the result of adding FFFF to 0, or adding 0 to FFFF gives back FFFF, which is non-zero, so the 0 flag is a 0.
But when you ran it the first time, you were adding...
Did it pop up?
Yes.
Okay. Well, I didn't pay attention, so but because I did not pay attention, I did not point it out. Let's do it again, but this time I will point it out. It's easy enough to do it. Put a breakpoint on line 8, run the program, take a look at E flags, and you can see that this time the carry flag is set and the 0 flag is set as well because the result, which is also stored in EAX, is a 0. So are we doing okay with those two flags? The carry flag, which is the carry from the most significant bit, and the Z flag, which means is the result of the previous operation, a 0. Yep.
So in this case, 8F, the number is being interpreted as a signed number?
Well, you can see that SF is not here because the sign flag is a 0. because we have 0 as the result, and the sign flag of 0 is 0.
Well, in order for that arithmetic to make sense, though, f of f would have to be -1, and then you add -1, you get 0.
Correct.
Which is why you get a 0 flag there.
Well, anything that gives you 0 will give you a ZF here. If you add 0 to 0, it will give you a 0.
Okay. So if it were an unsigned number, then it would be an overflow, right?
The overflow is going to be indicated by the CF because you have a carry from the most significant bit.
And then the ZF wouldn't be there. And the ZF wouldn't be there, the 0 flag, if
Well,
it were a signed
when
number.
you have overflow, it doesn't always give you a ZF though, because you can add 2 to FFFF, which also overflows. But in that case, ZF is going to be a 0 because it is non-zero. The end result is non-zero.
If it overflows, but the bits are all 0, the 0 flag will still be set?
Yeah,
Okay.
because the Z flag only looks at the result bits itself, not counting the carry flag from the most significant bit.
Okay.
And that was another hint. Go ahead.
How come it doesn't have the overflow flag even though it did overflow?
Ah, but that's because overflow is signed. Overflow is a signed interpretation. We'll talk about overflow when we get to that point. Okay, that's a good question. So keep in mind of that question. I'll answer that question. Okay, so far we have only talked about 2 flags, the carry flag and the 0 flag. Are there any questions about those 2? Okay. Now we don't quite know how to access those flags other than debugger at this point, but later on at some point we'll talk about conditional branches, and then those instructions will be able to access those 2 flags, and along with the many other flags at that point. So the next one is the Z flag. We talked about this already. And now we have the sign flag. Well, the sign flag is really quite simple. It is the most significant bit of the result of an addition. Okay, so if you have a 32-bit number, it's bit 31. If you have 16-bit add, using add W, is bit 15 of the sum. If you have 8-bit add, which means you have add B, add byte, then it's bit 7 of the result. So it is just a mirror. This is nothing more than a clone of the most significant bit of the result of the add instruction. Okay, any questions about this one? We actually saw it in action too when we ran the other exercise. Okay. Any questions? Yep, go ahead.
Flag checks to see if the most significant bit is a 1 or 0.
Yep, it's just a copy of the most significant bit of the previous add instruction. Okay. All right. So all of these are fairly straightforward. The 0 flag just reflects whether the result is 0 or not counting the carry from the most significant bit. The carry, the C flag, is just the carry of the most significant bit. The sign flag is the most significant bit of the result. Those are fairly simple. The next one is going to be a little bit confusing, but there's an easy way to look at it. Because we have the O flag. O flag stands for overflow. This flag is kind of fascinating because it is sign-based. One way to look at this is to say the overflow flag is set or has a value of 1 if and only if the sign of the result makes no sense. Okay, what does it mean by that? Well, let's go through some examples here. You will get your homework assignment next, that has to do with, all of this stuff here. So this is the one that particularly needs some attention. So we'll go back to my text editor here, and we'll talk about, whether the sign of a result make any sense or not. Instead of using 8-bit, well, I guess we can use 8-bit, but let's go ahead and use, just 4-bit numbers. Okay, we can illustrate everything using 4-bit numbers. Let's talk about 3 plus -1. Okay, this is the base 10 version, and then we want to look at the base 2 version. What is 3 in base 2 as a 4-bit number?
0, 0, 1, 1.
What is -1 as a 4-bit number? Okay, so we'll go ahead and add these 2 numbers. 3 plus -1 is 2, and over here we have 1 plus 1, which is 0 with a carry. 1 plus 1 is a 0 with a carry, and then 0 plus the carry from the other digit is 1. This one is going to be a 0, this one's going to be a 0, and then we have one extra carry, here. So we'll just go ahead and say that C equals 1, because the carry is going to be a 1. We have one extra carry at the end. Okay, let's talk about whether the sign makes sense or not. We have a non-negative number adding to a negative number, ending up with a non-negative number. Does that make sense? Not even looking at the rest of the bits, just looking at the sign of the two input numbers and the sign of the output. Does that make sense? You're adding a non-negative number to a negative number, you end up with a non-negative number. Can that happen? Well, yeah, it can happen. Okay. All right. Let's try another example. Let's try this one. -1 plus -1. When you look at it as binary numbers, -1 is 1 1 1 1. This is also 1 1 1 1. And then when you add up these two numbers in base 10, you have -2. And then when you add it in as a binary number, this is a 0. And because of a carry from the previous digit, all of those will be 1s, and you end up with a carry of 1 as well. I was using VI commands, and you can see the colon. All right. Well, does that make any sense? Let's think about it. We are adding a negative number to a negative number, ending up with a negative number. Can that happen?
Yes.
Yeah, it makes sense. Okay. So let's try one case where it makes no sense. Okay. So we'll go ahead and say we are adding -4, okay, and -5. Okay. Doesn't seem to be very big values. I mean, they seem to be somewhat reasonable values. And then we'll go ahead and just say the result in base 10 is -9. You know that. Okay, -4 as a binary number. How do we represent -4?
1 1 0 0.
It's 1 1 0 0. And -5 is going to be 1 less than that, so that means it is going to be
1 0 1 1.
1 0 1 1. And it's easy to double check because 4 itself is 0 1 0 0. When you take the negation, it becomes 0 1 0 0. It becomes 1 0 1 1, and then you add 1 to it, it becomes 1 1 0 0. And then the next value is 1 less than the first value. If you subtract 1 from 1 1 0 0 as a base 2 number, you get 1 0 1 1. So everything works out. It makes sense. Okay. So the question now is, when I add these two binary numbers, what do we get? Well, the answer is not that we are not getting anything back. We're just not getting anything with the sign of the result. Makes no sense in this case. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is a 0. And then we end up with a carry of 1. But remember, this extra carry, we don't care. We only want to look at the sign of the numbers. We have a negative number adding to a negative number, ending up with a non-negative number. That makes no sense. So in this particular case, the overflow flag will be a 1. In the other two cases, the overflow flag is going to be a 0 because the sign of the result makes sense. Okay, is that okay so far? I have one more case, where you can have an overflow of 1. Let's try the positive side of 4 and 5. Okay, 4 plus 5 as positive values. It's 9 in base 10. So the question is, what is happening when we do it in base 2? 0 1 0 0, 0 1 0 1. And we look at the result. That's a 1. That's a 0. That's a 0, that's a 1, and the carry, if I want to say something about the carry flag, is a 0, okay? The sign makes no sense. The sign of the result does not make any sense because we have a non-negative value plus a non-negative value ending up with a negative value. The sign of the result does not make any sense. Okay, So in the last two cases, the overflow flag is a 1. In the first two cases, the overflow flag is a 0. Yep.
Does this basically tell the assembler that, or whatever else, that when you're adding these to know which number is actually supposed to be a negative or positive when it's translating them? Like if you had to convert that number after adding the numbers together, you have to convert back to the decimal. Would it give you actual negative number or give you a positive number?
Well, in this case, the sign makes no sense, so I won't even try to convert it back to a signed number, because it tells me that the result of the addition ends up with a value that is out of the range of values that I can represent as signed numbers. Yep.
Yeah, that's kind of what I was going to ask. The overflow flag won't be, it can only be set if the addition exceeds the range of the
Signed interpretation.
Yeah.
Yep. Whereas the carry flag means it is out of the range of a unsigned interpretation.
Unsigned interpretation.
Yep. Okay.
So, what if you wanted to get a sign? What would you get? Would you get an error at this point?
There's no error. There are only flags. There are no errors.
Throw flags on the field too.
Okay, so as far as the process is concerned here, let's work out the 4 flags that we have talked about so far. The Z flag is going to be a 0 because the result is non-zero. The C flag is a 1 because there is a carry from the most significant bit. The sign flag is going to be a 0 because it is really just the most significant bit of the result. And in this case, the overflow flag is also going to be a 0 because the sign makes sense. Let's take a look at this case here. 0 flag is going to be a 0 because the end result is non-zero. The carry flag in this case is a 1 because there is a carry from the most significant bit. The sign flag is going to be a 1 because in the result the sign is in fact the most significant bit is a 1, and the overflow flag is also going to be a 0 because the sign makes sense. In this case, the 0 flag is going to be 0. The carry flag is going to be a 1. The sign flag is going to be a 0. The overflow flag is going to be a 1. And in this case here, we have Z equals to 0. The carry flag is a 0. The sign flag is a 1. And the overflow flag is also going to be a 1. Okay? Is that kind of making sense?
Yeah.
Okay, go ahead.
For the second to last one, what's the sign flag 0, not 1?
You mean this one?
Yeah.
Because the sign flag is the most significant bit of the result. It's just a copy of that. Yep.
So, in accordance to your wheel, if we did any other addition between two negative numbers and we got below -8 or -8, we would not have an overflow.
If you end up if you do the base 10 version and you end up with a value that is less than -8, then yes, the overflow flag would be a 1.
Okay.
Yep.
No,
Go ahead.
I answered my own question.
Oh, okay, great.
So those flags, the overflow flag will turn on every like 8 numbers. They'll turn on and off every 8 when you're adding.
When you run out
Because
of
the wheel.
when you run out of the values that you can represent, then in the signed interpretation, then the overflow flag becomes a 1. Okay. Yep.
Okay, so what I've noticed, and I don't know if it's just the examples you used or what, basically when the overflow flag and the sign flag, if you add them together, will tell you whether or not it's negative. Because if it's negative, you'll get a result of 1, but if it's not negative, you get a result of 0.
There might be a relationship there. I haven't really looked at it that way, so I can't really answer the question.
Okay.
Yeah, but I can try to work it out, figure out whether there is a relationship, direct relationship like that or not.
Okay.
Sometimes we look at a pattern and we think there's a certain relationship, but it may not be there. Like if you can find a counter example where that does not happen all the time, then you can basically say it's not a particular pattern. Okay. Are we doing okay so far with this? Okay. Very good. So the overflow flag is, there's also a way to represent the overflow flag just using logic gates. Let's take a look at these combinations here and see if we can figure out a way to look at the overflow flag and say, okay, if we want to use an expression to say the overflow, to express the overflow flag, what is it? Okay. We'll go ahead and use just the most significant bits of the three numbers that we want to deal with. Okay, so let me put a little legend here. A is the most significant bit of the first number. Okay. In this case, MSB has a lowercase b for most significant bit. When I use MSB with the uppercase b, it is most significant byte. Okay, that's a fairly well used, often used convention. B is the MSB, the most significant bit of the second number, and then we'll say S is the MSB of the sum. Okay, just notations. All right. So when do you think the overflow flag should be a 1? There are two cases where it has to be a 1. When we add a non-negative number and another non-negative number and end up with a negative number, then the overflow flag should be set. Right? Okay, let me. All right. Is that making any sense so far? That's one case where the overflow flag has to be set. What is the other case where the overflow flag has to be set? We have a negative number to begin with, another negative number, but the sum is non-negative. Okay? And then we just put a disjunction here, and we got it. It looks kind of counterintuitive. Not A means that A is a 0. When A is a 0, that means the first number is non-negative. Not B means the most significant bit of the second number is going to be a 0 as well, so we have two positive non-negative numbers. When we specify sum or the S bit as by itself, that means it's a 1. So we have non-negative. Okay, let me just use the mouse here to highlight it. So in this case, this fits the pattern where we have a non-negative first number, non-negative second number, and a negative sum. Well, the sign makes no sense, and therefore, this is one reason to set the overflow flag. In the second case, we have a negative first number, a negative second number, and a non-negative sum, which also makes no sense, and that's the other reason to set the overflow flag. So that's the other way to look at the overflow flag, as bitwise operations using the most significant bits of the two numbers as well as the sum of the operation. And this part is important because when if we just look at things from the perspective of is the sign making any sense, you cannot translate it into silicon. I mean, that's a human thing to say whether the sign makes sense or not. But this we can translate into silicon because we have NOT gates, we have conjunction or AND gates, and we have disjunctions or OR gates. So now I can specify everything in terms of processor design elements. Yep, go ahead.
As far as the 0 flag goes, when is that actually useful?
The 0 flag is not that useful for additions, but it is much more useful for subtractions. Okay. Any other questions about the flags at this point? Okay. Let me make sure I save this file again. I think that's all for addition, so we can now move on to, okay, how do I see these flags? But we know the E flags can see it too, so this part is really kind of obsolete. You don't really need to read this part here. All right, so we'll move on and talk about subtractions. Subtraction is also comparison. Okay, so we start with the same thing, the rule.